All right, guys. So welcome to another lecture. I hope you will, if you're just tardy at calculating it, but that soon the procedure is going to be very fast. Okay. James, I will respond to your question later, I suppose, right? It will take me also some time to read it. So, yes, I have, as you know, a lot of people are gathered in my fold, just like you are, right? Yes. Sons and daughters.
I get it.
Yes. Okay, guys. So here is the situation. For this example, poker hand is played with 5 cards. So you have altogether 52 cards. I hope you know that. Yes. So what is a card, at least to a person like me? By the way, do you know, guys, I'm not sure if you're reading Master and Margarita. The usual book for this class is Dostoevsky's The Gambler, right? For the very important reason that Dostoevsky liked to play and wrote The Gambler, because he was in debt. So a card for a non-player like me has 2 numbers. It has a front number 1 through 13, and it has the suit number, which I label 1 through 4. It's up to you how you decide to label the suit numbers, but let's agree that we have a code. 1 means heart, maybe 2 means spades. It doesn't matter, right? So we imagine we have fixed a code when we do that situation. Yes. So when I report a card, it's enough to report 2 numbers: the front number 1 through 13 and the back number that identifies a card uniquely. So what does it mean that we are selecting randomly 5 out of 52 cards? Right, so that means that if we make a simultaneous selection, you remember we can make simultaneous selection or sequential selection. These will not influence the end result in probability. But if I decide that I make simultaneous selection in my sample space, my success report must also have the same format. It must be simultaneous selection. You understand that? Yes. You cannot mix those two. So this is my protocol for the sample space. Just select 5 cards and put them in order. They have population numbers 1 through 52. Put them in order. That's denominator. Understand? So there are 52. Choose 5 ways of doing that for the denominator. I think most people know that. Now, how would I designate success, guys? Right, so success means that I have cards that if I list them in order, the numbers go 1 through 5 or 2 through 6 or 3 through 7, where you remember the front numbers are 1 through 13. Yes, and the suits are not the same. So to specify such a sequence, it's enough to mention the first number in that sequence, the smallest number in that sequence. Yes. So if it's 1 through 5, the smallest number is 1. If it's 2 through 6, the smallest number is 2. And in that box, that's my document, I will place the smallest card number. And that means because it's a sequence in increasing order, all the other numbers are determined. You agree? So how many inputs can there be in this box? The smallest number has to have additional 4 numbers going beyond that, exactly 4, right? So what we can do is we can take 13 minus 5 plus 1. That's the way to calculate it, right? Minus 5 plus 1 because, well, I hope you understand that plus 1 part, guys, yes? It's when I take 13 minus 5, I go too much far back. I need to move 1 unit upwards. Think about it. Good. The last card is 13. I need to, if I say minus 5, I am going to the card prior to the last, so I add 1. Good. So you understand that the number is 13 minus 5 plus 1. Now, once they are here, we already know in order what are the front numbers. One, let's say if the box here is filled with the number 1, then my cards are 1 through 5. I don't need to mention them in my form. Yes? Because this is only the success form. Numerator is only counting how many successes. So that's my success form. So all I need to mention are the suits. So what are my suits? So each of the 5 cards independently can have any of the 4 suits. There are 4 numbers, right? So that would be 4 to the power of 5. Do you agree? In general, there are 4 to the power of 5 ways of filling this box out, but I am not allowed to have the same suit on all cards. That's part of the condition. That's why I subtract 4, right? So I cannot have the number 1 everywhere, or the number 2 everywhere, or the number 3 everywhere, or the number 4 everywhere. So there are 4 possibilities where that happens. So that's why I subtract 4. Are you all clear? Wonderful. That's brilliant, guys. And you can, of course, not just by my explanation, the goal is you will be able to construct such documents. We are soon approaching the end of chapter 2. And of course, we don't want our prior exams to go to waste, of course, right? I mean, I wrote those questions not in vain. We have lots of examples and lots of questions that we will all solve before we get the exam. And we will work at it in office hours together and see how the solutions are presented. Am I right? The only reason those are not your exams immediately because some of those questions were compromised as they were posted online and I found it, right? Which will not happen this semester, of course. Yes. And this is the probability. I've seen this result and some people write 10 instead of 9, but that is a sort of, I'm not sure what people consider sequence, in ordered sequence. Maybe, I'm not sure where the 10 comes from. So I think the actual answer is supposed to be 10 instead of the 9 that I wrote here, but you don't have to worry about it. I don't play this game. I'm not sure what they mean sequential, right? So there is one extra option that I have omitted. Here, guys, is your next task. You can try to solve both if you want to, or solve A. So here, I want you to calculate the likelihood of exactly 1 pair. And in the second part, exactly 2 pairs. Do you understand what a pair is, guys? It means that the front number, or the actual card, let's say maybe it's Jack and Jack, or it's 10 and 10, or it's 1 and 1 if there is a 1, I don't remember, right? 2 and 2 basically, right? So and the other 3 cards are distinct. So yes. So you understand what I'm saying, guys? So so Andre knows this game, I think, right? So good, Andre, right? Andre is good at this, it appears to me. So here, you understand, guys, what the question is? In my mind, it's just front numbers. We have 2 numbers that repeat, 2 front numbers that repeat, and the other numbers do not repeat. Understood? Calculate.
Oh, quick question.
Yes, James?
So I put it like this, right? So we know that we still looking for the probability of these five cards, right? But we're also looking for pairs, right? And we know that there's four types of cards in a deck, right? So you gotta get four types of each number, right? Am
Oh,
I
I'm not sure what you mean by four types. So here you're supposed to get, let's say, the number two, two, and maybe three, four, five, or whatever the numbers of the cards that are available, right?
never mind, I misread the question.
Yes. So there is part A and there is part B. Yeah, Andre, you are correct for B. Okay, Nora. Very good, Nora. Jennifer, nice. And then, of course, think about B when you're done with A. So, I'm not sure, Sarah. I am not recognizing what you wrote. I need to think about the strategy. What was that? So you see, guys, when you write your exam, of course, over the comments, it's hard to do. But on the exam, you will indicate your protocol so that it will be faster for me to figure out whether you are right or wrong. All right, let's work with, shall we work with A? Or do you want to work a little longer before I speak? All right. I suppose let's work through A. Ready, guys? And we can discuss more of those solutions. Okay. Let's see. We'll first read what somebody said here. So Sarah, you see, first thing you say choose a card of from 52. Let me see for a second before I speak. Sorry, let me not say that. Yeah, so Sarah, you will have a situation where you have more than one pair. Do you see that? Because you select other cards, but you don't eliminate. So you say you eliminated the first pair, but you don't eliminate other possible pairs. You agree? So let's work it together. Okay, guys, so very important that you come up with a protocol. That's what I mean. It's very, very easy to make a mistake or to not see something. And you understand the idea of the protocol is that before I count anything, I have a code. And I know that if I read the code, I know what was the outcome. And if I know what was the outcome, I can put it into the code. Then I can be sure that I count correctly. Okay? That's why I'm saying don't trifle with the Kafka protocol. So here it is, guys. Obviously, for the sample space, it's 52, choose 5. You agree? So now I need to have a success protocol. What happened if I if it happened that I pulled out the cards and had exactly one pair? Okay, so if I had exactly one pair in my document, I say, tell me what is the number on the pair. So a pair number. You understand? And then because we imagine the suits are ordered 1 through 4, once I tell the pair number, I tell you which suits came about. You understand? So once I know the pair number in which particular suits, then I know the cards. I know the pair. Do you agree? So this is how I work. So pair number, it's 1 out of 13 cards. This document can be in order. You put smallest pair, largest suit, right? Smallest suit, largest suit. So there are 4 choose 2 possibilities there. So it's 13 choose 1 times 4 choose 2 to fill those 3 boxes. Next, I need to know which numbers came for the remaining cards. So I am not able to access the number that was picked here. There are remaining 12 numbers. Out of those 12 numbers, I pick 3 because they have to be distinct and I place them in order. Okay, so because what we are saying, only one pair came about, not 2 pairs, right? But only one pair came about. So I mentioned what is the number on the pair. I mentioned the suits corresponding to the pair, and then I mention the remaining numbers that are solitary and their corresponding suits. So here is the smallest number that's not a pair. There is the next number that's not a pair. The third number that's not a pair. So that's why we have 12 choose 3, 4, 4, and 4. They can have they're different numbers. They can have any of the 4 suits. So my numerator, the success protocol, is 13 choose 1, 4 choose 2, 12 choose 3 times 4 cubed divided by 52 choose 5, which is this number. Okay? Clear? Yes, Sarah?
Professor, can you again explain why we have 4 choose 2 here?
Why we have here 4 choose 2? Because of this box. Do you see this box? Now, we have a pair number, right? One pair number. So there are 2 cards of the same pair. There are 4 cards that have the same front number, right? So let's say take the front number 1. I imagine that all the cards are listed numbers 1 through 13. Take a card of number 1. It has 4 different suits. Do you agree? So you cannot have. You cannot have. Okay, let's see. I'm also confused. So you cannot have three of a kind. You see, Aaron, so it's a different question. Notice I say B, C, and D are not the same. So it's not just two pairs, but it's two pairs. And if I said otherwise, of course, that's not a good document, right? So you're right. This document, you have to be very specific. Am I allowed to have a triple, right? Here, I did not allow myself to have a triple. The document would have been even simpler if I allowed myself to have a triple. Here, I only have one pair. Everything else, every other number appears once. That's the idea of this document. You see, I mentioned it here, but you are absolutely right. If I didn't say this, this document isn't valid. Good. So guys, do you see back to that FNU? You see there is one card, the number, and here I have a pair. Right, a pair on the back. You see, so there are four possibilities for each of the card. Two of those possibilities actually were picked because I picked two cards actually. You see, the pair number means that I picked two cards, which means that they are distinct not by the front number but by their suit. So they must be of distinct suits. So which suits are those? I take 4, choose 2. You with me, guys?
I see. Thank you, Professor.
Yes. You see what I'm saying, right? So it's I don't only think about the code, and of course maybe some of you can solve this question very rapidly without doing the document. My point is, if there is anything to teach here, is how can you be sure that you're correct? That's my best way of being sure that I am very, very precise on how I list the success before I even count it, and how do I describe it. Clear? Okay, guys. So if it's clear, let's do problem number B. Now we have two pairs. I'm going to give you another 2 minutes. Two pairs and one singleton. And be very careful. Two pairs, guys. So Jack, you are making a small mistake. It's an interesting idea. So Jack said something very interesting. Let's remember that, okay? Once we get there, I will explain your mistake, Jack. Thank you, by the way. It's very good that you reminded me of it. Guys, only Kafka protocol will save you. Believe me, right? That's the only thing. It's like witch trial, you know, I just was watching it, German witch trials. What they did is they submerged the witch, and if she drowns, drowned by water, then she is not a witch. But if she floats, then she is. My point is only bureaucracy will save your soul. Yes, Jennifer, you are right. All right, let's look at it together, and then we ask, yes, exactly, Jack, you found it. So let's look at the document that I produced, guys. You see, so to avoid mistakes, produce the right document. The success document I have here is, if I got exactly two pairs, I can list by the front number. What was the small front number on the pair, and what was the larger number on the larger pair? You understand? And if I found those numbers, I will list them in order. You imagine that you find the cards, and then first thing I do is I find the smallest pair, and I list the numbers of the smallest pair, and I find the larger pair, and I list the number for the larger pair. And that goes into this document, okay? That's why I wrote the document this way. So you have to have smaller number here, larger number here. That's 13 choose 2. Now, here are the suits for the first pair. Do you see it? Oh, if you see, it's 4 choose 2 suits for the first pair, and no matter what were the suits for the first pair, there are 4 choose 2 suits for the second pair. I list the suits also by order. I imagine, so I use a lexicographic order, dictionary order. I first list them by first number smaller than second number, and then comparing suits, I list them from smallest suit to largest suit. You understand how I sort my cards? So if you see first pair, you flip around, you see that the number to my left has the smallest suit number, and to the right, the next smallest, right? Then the same thing here. Clear? And then it's up to you how you do the remaining one. So you can say remaining card is, we eliminated altogether, we cannot access 8 cards. Right, we picked, we cannot access 8 cards, 4 corresponding to the first pair, 4 corresponding to the second pair. So we can say remaining card is 52 minus 8, choose 1. Or you can list the remaining available number and the remaining available suits. It's up to you how you do that, okay? You can make different documents. Now, a very common mistake that people do, sure, you can do it separately, Jack, right? You just have to be careful, right? So a common mistake that people do is something like this. So they say 13, choose 1. Maybe the suit is 4, choose 2. So that means we pick the first pair and we assign the suit numbers to it. And then we have 12, choose 1, 4, choose 2. And forgetting about the remaining cards. You understand what's wrong about doing this? What's wrong about it? You know what's wrong about it is here, first of all, you are producing a sort of order. What do you mean by first suit? It's very unclear. What is first suit and what second suit, right? So for example, in your procedure, it means, if you write it like this, it means, let's say I can get the number 1 and maybe a suit, whatever the suits here, and the number 2 and whatever suits here. Or I can get 2, whatever suits, and 1, whatever suits. So I overcount exactly by 2 possibilities, you see? So if you do it this way, Jack, you have to divide your result by 2. Which, by the way, I mean, you always have to think about the document, because otherwise it's very subtle, very confusing. You have to have a document in your mind, in front of you, so you can explain how you presented your success information. Good? With me, guys? All right, guys, this one is, and again, don't be, again, guys, if you are not getting it on the first trial, it's okay. It took me a long time. I'm much worse than you, I think. It's not natural to me. But I developed some ways to bypass it, and hopefully you would like those ways. So what about this question, guys? Poker dice is played by simultaneously rolling 5 dice. What is the probability of 2 pairs? Can you come up with an idea of how to do it? You understand? 2 pairs means that you have 2 pairs. I'll give you 4 minutes. It's a short time, but what can I do? By the way, it's too bad you missed what, when, where. We were killing. 4 questions solved correctly. Yeah, I don't think you're right, Sarah. Jack, your expression doesn't seem to indicate which die displayed which numbers. You're telling me which numbers came about, but not which die displays which numbers. Therefore, it's wrong. I'm not sure, Andre. I mean, I think that what you wrote is not completely right, but I will check again in a moment. All right? Because I think it's not clear. So you have 6 choose 2, two numbers. Which of those dice display? Maybe I'm wrong. This I don't want to throw it at you. Maybe you are not wrong. I'll think about it. You have to be careful, guys. Must be a protocol. And of course, you understand that when you submit your work, so that it's much easier. See, I want to spend as little mental energy as possible grading your exams, right? I don't want to be guessing the process, right? Or thinking about the process you created. I want to see it explicitly. Understand? So on the chat, it's hard to type, but on my exam, you will write something similar to what I do to indicate exactly how you carried your calculation. I want a Kafka protocol. All right, let's carry the calculations together, guys. So let's try to understand what's the situation. So for this problem, as many of you noticed, it's nice to keep each die. I can imagine that each die is of a different color. So I know which die displayed which number. Yes. Okay. So then I imagine that if I imagine them as distinct, I imagine reporting any outcome. This is a protocol reporting any outcome as saying what came on die 1, what came on die 2, what came on die 3, and onwards. You can see that each of them has 6 possibilities, so there are 6 to the power of 5 overall possibilities. Clear? That's my overall protocol. Now, what is my success protocol? Here is the success protocol that I considered, okay? My success protocol was this. So first I report what were the pair values and then what was the single value, right? So there are 2 pair values that I should see and a single value. You see how I break it apart, right? So when I have a success, I report, let's say maybe I have 2 copies of 2 and 2 copies of 4. So I will write it in order, 2, 4. And then what was the remaining single number that I received? I put it over here. So how many possibilities are there to fill this box? There are 6, choose 2 possibilities. How many ways to fill in that box? It's 4, choose 1 possibility. Yes? Also, another recommendation, if you can do it in several ways, that's also nice. In several ways, you produce the same result, less likely that you are wrong. Now, what about this situation, guys? So now we have this multinomial coefficient. Remember the dragons and the knights, right? So you see, if I just have this portion, I don't know which die displayed which number. So I have altogether 5 dice. Which display the smaller pair? 2 of them had to display the smaller pair, right? 2 of them had to display the larger pair, and 1 of them had to display the number 3. You understand? So what is this 2? Those are the 2 dice that display this number. So for instance, if I have this code 2, 4, 3, 1, 3, 4, 5, 2, what does it mean? Look at it. If I read this code, I can right away see the dice. Do you see how I'm picturing it, guys? You see the dice? Look at it. 2 and 4 were the numbers displayed in pairs. And the number 3 was displayed as a single one, right? So then look what happened. 1 and 3, one die number 1 and die number 3 display the number 2. Here it is. 1 and 3 display the number 2. Now 4 and 5 display the number 4. 4 and 5 display the number 4. The die number 2 displayed 3. Understood? Right, so it should be very, very precise how you carry it. Okay, Andre? I mean, so the first thing, of course, when you, yes, so let's say you say 0.23128. So let's see if that's the same. Yeah, so Andre, of course, as I mentioned, right? So you're correct. Good, right? So I just had to think of how you do it. But when you give me the protocol, then I know for sure that you are right. If I see how it will take me less time. You understand? To verify that you're right. And you understand if it takes me more than a minute. Yes, the dragon part again, the dragon part is here, Jack. You see, look at it. What are, you understand why I'm saying multinomial coefficients, right? We are assigning destinies to the dice. Which die display which number, right? So if I just know the numbers, Jack, you mentioned how to calculate just finding the numbers. If I know just the numbers, that's not enough. Which of the dice displayed which numbers? So I have 5 dice, right? So first 2 dice, they go to the fate of displaying smallest number. Okay, the dragon is smallest number of the pair, bigger number of the pair, and singleton. Yes. You can solve it, I mean, quickly. Just 5 factorial over 2 factorial, 2 factorial, 1 factorial. I mean, you can just carry out the calculation that you like, right? So you understand, guys? I mean, it takes a little time to figure out whether somebody is right or wrong. So you understand? I mean, if you have 30-something students, for every question, it's really, really, pain in the head. Okay, so I want you to display your procedure like I do. Understand? Look how explicit I do that, right? If I do it, you can do it too. Wonderful. Here is your comprehension check, guys. We have 9 dice. They are simultaneously rolled. What is the probability of getting 3 pairs and a triple? It's like the question before, you understand? We must have exactly 3 pairs and 1 triple. Go ahead. Okay, if no, looks good to me. Okay, let's see. Erin, very good. Same thing as Fnoder. Alan, very good. Sarah, let's see, 6, choose 1. So you first say which is the triple, right? And then you say 5, choose 3, which are the pairs. Amazing, very good, right? So Sarah did it differently. It's always nice to see it. It avoids my paranoia a little bit when it's different solutions. Yeah, good. Yes, Sarah, I will in a second, right? So remind me if I once I explain this question, if I forget to explain about order versus no order. All right, any more? All right, let's try to solve it together, I suppose. Yes, guys? So this is my protocol. Sarah's protocol would have been a little different. Fnu's protocol, and I presume Erin's, would have been the same. Yes? So here is the situation. So first I select the pairs. So here I list smallest, middle, and largest pair once I select them. So it's 3, choose 1. Now the number on the triple is 3, choose 1, right? Once I have the pair, there is only one number of the remaining 3 that could be the triple. And then what do I do, guys? So here I assign the dice in order from smallest to largest that take on pair number 1. That is smallest pair, guys. When you say pair number 1, you have to be very clear. What do you mean by pair number 1? I mean smallest number. Then here, it's the middle pair. Here is the large pair. And here is the triple. So it's 9, choose 2, 2, 2, 3. And my probability is 6, choose 3, 3, choose 1. You know, the multinomial coefficient of 9, choose 2, 2, 2, 3. Which you all know how to calculate, right? So now let's talk a little bit. Why do I have to emphasize pair order, Jack? To differentiate, well, for many things. I mean, first of all, how would you present the solution? You understand, when I read a code, that code presents the solution. If I cannot see how from the code how the solution is presented, then I don't see the solution. I don't see the success, right? right? So if there, so I decide this way. So if there were 3 pairs, there was the smallest, middle, and largest pair. So I present smallest, middle, largest first. Any other ordering is okay as well, right? It's just you have to be very precise on the ordering, then you count it correctly. Now, Sarah, you speak about some sort of when do you think of order and we're not of order. Well, so we spoke a little bit about that when we spoke about sequential sampling versus simultaneous sampling, and saw that the result must be the same. It's also, I think, intuitive that the result should be the same. What does it mean random? Random means that there is no preference to any pattern to occur. Now, if you select cards in order, for example, if I first select one card, then another, then another, then another, I select the 5 cards or in order, then I can afterwards list them any way I like. I can, once I selected my cards, I can present my cards any way I like. I can then regroup them to follow the dictionary order if I want to. You agree? Now, if there is no preference in how the cards were selected, it's intuitive that there will not be preference in the actual list of cards that I produce, right? So, for example, if I sampled card with denominations 1, 2, 3, 4, and 5 in any order, I mean, this front denomination will be as likely as any other front denominations. Yes. So you're always free to. So again, make sure that what you do there is you see that numerator and denominator are done the same way. You're always free to assume that there is a distinction. What was first, what was second, what was third. It's metaphysically it seems true, right? Because metaphysically it seems that you noticed one card first, then you noticed another card second. You can always imagine that there is order if you want to. Okay. But sometimes it doesn't matter because the patterns in the numerator and denominator will cancel out. Okay, so you must always be very careful about choosing your sample space, and then once you chose your sample space, you report the information, success or not, in terms of the sample space. Okay, I hope you understand what I mean. So if you did, so why did we select order for the dice? Because it's convenient for me. Right? Even if the dice look the same, because they are not in the same place at the same time, there must be distinct. So there must be something about the dice that make them different. I can imagine they are colored differently. So I can distinguish what's die 1, die 2, die 3. I can always imagine they are distinct. You see what I'm saying? And that's convenient for this particular problem to do that. So whenever it's convenient, I can imagine that objects are distinct. Because they are always distinct, it seems, right? Always, no matter how close they look alike, if they are not in the same space, at the same time, there must be some difference about them, and that's philosophy.
So just to clarify, the reason that we didn't have to account for order in the card problem was because in the denominator, we also used 52 choose 5.
Yes. Once you selected 52 choose 5, numerator cannot indicate what was first, what was second, what was third, because it's not counting the sample space. When you say 52 choose 5, you now no longer know which card was selected first, even if there was a selection first. So it's as if they were selected simultaneously.
Okay.
You see? You can imagine that their selection wasn't simultaneous because even if they were picked simultaneously, maybe as you were looking at the cards, you noticed one card first, then another, then another, then another. You understand? So you can always imagine that there was order in your selection. But it's intuitively clear that that will not affect the result, because if there is no preference in order, there will not be preference simultaneously. So it appears. We proved it a little bit, right? Make sense? But always count the same sample space. Once you fix your sample space, your numerator, your success report must be in terms of the sample space. It cannot be something else. Okay, here is another example, guys. Maybe a little bit more difficult. Let's see if you can do it. Are you ready? So now we have a game of bridge. In that game, there are 4 players and 52 cards are divided equally among the 4 players. Now, I want you to calculate the probability that one of the players receives all 13 spades. You understand? We can do it in many ways. So let's calculate it. One of the players receives all 13 spades. Yes, you can hear him. Now you want to see him, huh? I should show you a magic trick afterwards. Now let's see if I can do a magic trick. You think about this question. Abracadabra. And look what happens. I can turn cats to, I can make them black. See it? The magic of mathematics. I can also turn them into orange. Let's see what we have there. If you want to see, by the way, the magic, how I turn cats to orange or to whatever colors, it's complex analysis, the cubic equation. If you want to, I'll show you how it's done. Are we ready? Why is it, Sarah, 13 factorial over 52 choose 13? Numerator is produced how?
Well, I thought you have 13 cards to choose from, and like there are 13 options in the first slot, 12 in the next slot.
But in the denominator, you don't do it in order.
Doesn't it produce the same thing?
No.
Oh, then never mind.
Because think about it, the numerator means you select 13 cards simultaneously for some person, right? First of all, it doesn't mention which person. So I look at it, which person got 13 cards, 13 spades or whatnot, right? So I don't see that. And secondly, numerator is order-based, denominator not. Do you see that?
Yeah, okay.
Right. You can correct it, you're close. All right, guys, a few more moments and we will solve it together. Okay, Nora, you're good, correct? All right, ready, guys? Let's do it together. Was it a difficult question? Or you just kind of got tired of answering it to me? Right? Oh, it doesn't matter. I don't know any of those games, Andrew, right? It's just they say exactly the same cards. Yes, okay. Well, guys, think about why is it confusing? That's my point, guys. I think you think, Mo, forget this old man. Let me not follow his Kafka protocols. No, guys, you follow my Kafka protocols. That's your ticket into the castle. Here it is. Guys, so I will show you first a more difficult solution, and then I will show you, for example, what I think, I forgot the name, Jennifer, what's the name? No, it was Nora, sorry, right? So what Nora said. Here is the situation, guys. So first of all, let's say RK be the event that player K receives all spades. So those are disjoint events. Do you agree? It's either R1 or R2 or R3 or R4, and there is symmetry here. You agree? So it's really the summation of PR1 plus PR2 plus PR3 plus PR4. Yes? All the way to, so now by symmetry, it's just like 4 times PR1 because PR2 is the same as PR1 by symmetry. You see, you feel the symmetry there, yes? So the result is 4 multiplied by PR1. Now here I decide that my sample space includes mentioning every single person, right? What everyone received. Now player 1 received all spades, so I know what he received, but I don't know what the remaining players received. So there are remaining 39 cards and 3 remaining players. Each of them has to receive 13 cards. So it's really this, it's really, so PR1 is 39, 13, 13, 13 divided by 52, 13, 13, 13. That's my denominator. In the denominator, I can list, here is what the denominator means. In other words, when I distribute the cards among four players, each player lists his cards by smallest to largest number. You understand? So I just imagine what's happening here. I didn't even bother drawing the protocol here. So that's the result. And if you simplify it, it's this situation, okay? But I can do something else. Look at it. I can say, well, doesn't matter what the other people receive. All that matters is what one particular guy receives. Because you understand? I think of the situation, forget about what happens. There is symmetry. Player one can receive any 13 cards, right? And each 13 cards are equally likely to be given to the player one. Do you agree? Any cards, right? So a simpler solution, one that reduces the sample space. You understand, guys? We are working with a different sample space. Would have been so. It would have denominator 52 choose 13, like what you wrote, Sarah. And here you would have 1. Right? There is only one situation in which those 13 cards are all the spades. Yes, out of all the possibilities of picking out cards, one possibility. So the answer is 1 over 52 choose 13, and that's for player 1. So if it's for player 2 or 3 or onward, so you multiply it by 4. Now, what you wrote, Sarah, you wrote 13 factorial. Now, what is the 13 factorial doing? What you see, first of all, forget about whether it's right or wrong. Where do you get it from, right? What is the document that gives you 13 factorial? It has to agree with the sample space that you pick, okay, guys? So the simpler solution possibly is 4 divided by 52 choose 13, where you reduce the sample space. If you want, guys, yes?
How did you get 39 factorial?
How did I get 39 factorial? It's just 39 choose 13, 13, 13 is this thing. It's 39 divided by 13 factorial, 13 factorial, 13 factorial. It's the formula for this multinomial coefficient from previous lecture, right? So if you guys want, after class, I can give you more of those practice questions and you can solve those practice questions. Let's try maybe, do we have time to solve for question B? Each player receives exactly 1 ace. Let's do it together. Each player receives 1 ace. So how can I think of it, guys? You see here, I just have the protocol in my mind. I didn't bother writing it out. So the aces, we have 4 aces. They're in different categories. There are 4 factorial ways of assigning the aces. There's ace 1 through ace 4. And there are 4 factorial ways of assigning those aces. Do you agree? So that's where the 4 factorial comes here. Now, each of the remaining players has to receive 12 cards, additional 12 cards. So it's 48 choose 12, 12, 12, divided by 52 choose 13, 13, 13. And once you calculate, you get this number. By the way, receiving all 12, all 13 spades is a very, very small number. You can see I calculated it here. It's very, very unlikely. Not likely for you to see it, right? Look how many. It's minus 12, so it's okay. It's less than 1 out of a billion, right? It's extremely unlikely. You will never see that. Good. Here is a comprehension check, guys, before you leave. So I changed the question slightly. 6 cards are sampled randomly from a regular deck of 52 cards. Calculate the probability of being dealt 3 pairs. If you cannot stay, guys, and you have to go, obviously don't feel pressured. I will answer this one more question there, and then we'll call it a day. Yes, Fnu, you're right. in office hours, we can practice more such questions if you're interested. Okay, I'll make up questions like this and you see if you can get them. Very good, Sarah. You did it. Okay, guys, let's do it together. What do you say? So I don't hold you. So here is my sample space code, right, where I list the cards. If I have cards 13, 15, 17, 51, 23, and 7, I have to list them in order. So that's 52, choose 6. Now, if I have 3 pairs, it means that I have to record the pairs maybe based on smallest, middle, and largest number. So it's 13, choose 3. Now, the first box here corresponds to the suits of the first pair. Now, first pair means smallest. You understand? When you say first, it must be unequivocal. The middle box here represents the pairs, or the suits for the middle pair, and so on. So that's 13 choose 3, 4 choose 2, 4 choose 2, 4 choose 2. And so I have this result, right? 13 choose 3, 4 choose 2, 4 choose 2, 4 choose 2 divided by 52 choose 6. Good? Wonderful. Now, I wish you a good night if you are not staying for office hours. Take care, guys, if you're not staying. And if you are, we can practice more such problems.